All right, we're going to go ahead and start for the day for our last presenter of the semester. With us today we have Dr. Marina Vance, who is coming to us from the University of Colorado Boulder. She's been there for about 3 years. Before that she was at Virginia Tech, and she's going to talk to us today about her work in indoor air quality. So I'll hand it over to Dr. Vance.
Thank you. I'd like to thank Dr. Bergen and the class for having me here as a speaker. I'm really happy to talk to you. I'm the last speaker of the semester, so get excited. So today I'm here to talk to you about 3D printers. Particularly, I'm talking to you about quantifying human exposure to everyday particulate matter. I don't know if you knew this, but 3D printers actually emit a lot of air pollution in indoor environments. As Dr. Bergen mentioned, I'm an assistant professor in mechanical engineering and environmental engineering at the University of Colorado Boulder. So first thing I'd like to do for this talk is for all of us to take a deep breath. And if I'm doing it, you can do it too. Yeah, okay. Congratulations. You all just inhaled 1 million particles. So that's what happens all the time, everywhere you go. We are in a typical indoor environment where there might be some cooking happening in the building. Maybe there's a toaster somewhere, some far away, and the ventilation system recirculates and those particles get everywhere. There's also particles coming from outside. So normally there's about 2,000 to 10,000 particles per cubic centimeter of air everywhere. If you're in a polluted, and we usually inhale about half a liter per breath. Maybe my deep breath was a little bit more, so I inhaled even more than 1 million particles. But if you're in a heavily polluted city, the concentrations can be even 20 times higher than that. So each breath, we're inhaling a lot of particles. We don't normally see them. The air has to be pretty hazy or smoky for us to really notice the particles, because the human eye can't really see anything smaller than like 100 microns in size, and I'll show you these are much smaller. So why should we care, right? So the reason I care about the research I do can be explained by just looking at a few news articles. So, for example, through this one we can see that poor air quality kills over 5.5 million people annually. So that means every year all of these lights are cut shorter than they should have been because these people have been exposed to air pollution for a long period of time. So in very polluted places, like in China, for example, some modeling studies have shown that people lose about 5.5 years. Your life can be significantly shorter if you live in a polluted place. But beyond mortality, air pollution can be linked to more subtle health effects, like brain aging, anxiety, and things like that. And finally, we were all actually kind of happy when this happened. Finally, the World Health Organization in 2013 recognized that air pollution in itself is a very, it is a toxic substance. So they categorized air pollution, outdoor air pollution, as a carcinogen, and then they evaluated particles separately as a major component of air pollution, and they also found that exposure to particles in the air is classified as a carcinogenic. And if you go back to these articles that I was showing you, it's like they all say air pollution in the title, but if you actually read the title, the article itself, you'll see that they're talking about particles. They're talking about PM 2.5 that I explained to you, particulate matter, small particles in air. So that's why I care about the work that I do, is studying your exposure, our exposure to particles in air. So what's the deal with particles? When it comes to particles, it's important to understand what they're made of, so their chemical composition, but also it's really important to understand their size, because most of the health effects are going to be associated to the size of the particles and the physics that those particles go through when we inhale them. So for that reason, this is a nice image from EPA that just puts everything into perspective. There are two sizes of particles that really matter for regulatory purposes for outdoor air pollution. We call them PM10 and PM 2.5. So if you start with, fine beach sand, about 100 micrometers in diameter, and we go down to maybe the thickness of human hair, which is about the same, about 100 micrometers in diameter. And then you go down to PM10. So these particles are 10 micrometers in size or smaller. Here are some examples. And these particles are known to be inhalable. So we actually might be able to inhale them when we breathe, of course, every day. And then you see these, the pink ones, 4 of them lined up here, represent PM 2.5. So these particles are called fine particulate matter. So all particles that are 2.5 microns or smaller are very important because if we inhale those particles, they can actually stay in the respiratory tract. And I'll show you exactly where. But there's another category of particles. If you just look at PM 2.5, you're considering most of the mass of particles that can be inhaled, but what I like to study is something called PM 0.1. This is not regulated, this is not part of the law, but a lot of researchers are focusing on the component of particulate matter that's smaller than 100 nanometers, so basically nanoscale particles in the air, and they're represented by the little black dot there. So if you're used to regulating particles in the blue range here, 10 microns in size, and all of a sudden we are starting to study PM 0.1. Many changes will have to be made in terms of regulation and monitoring and measurements because these particles are usually measured on a mass basis. As you can imagine, these particles amount to almost no mass compared to these, right? But these might end up having the biggest health effect problems. Just to put it into a little bit more perspective, this is sort of about the size of a flu virus, just to give you an idea. And the reason we care about the really small particles is dictated by physics. So particles get transported and deposited in the human respiratory tract. By deposited, I mean they just attach to a surface. And if they touch any surface inside your respiratory system, they don't come back out. They're basically stuck there. So we care about the particles that get stuck, and there are many particles that we inhale and then they come all the way back out. They don't really matter as much for health effects, of course. Really just the particles that end up getting deposited. So if we look at this chart here on the left side, you'll see the x-axis is the diameter of the particles, the y-axis is their percentage or probability of deposition in the different regions of the respiratory tract. So we are concerned about particles starting in about 1 nanometer. If they're smaller than that, they're really not called particles anymore because they're too few molecules making them up, so they're sort of gas phase. We don't really know what's going on here. And then up to 10 microns in size, as I mentioned before, right? So if you look at the top, you'll see that the particles that are the smallest, getting really, really close to 1 nanometer, they deposit in this region here, the nasopharyngeal, laryngeal region, so the upper airways near your head. This is where they deposit. And that's because these particles are so small that they're very prone to Brownian diffusion. So they're diffusing through the air, and as we're inhaling, they just diffuse to the walls. Particles that are too large, getting close to those 10 microns in size, or bigger than 2 microns, likewise, they deposit in the upper headways. And the reason that happens is because it's the opposite, not diffusion. It's because they have a lot of mass, so they're more prone to gravitational settling. They basically can't make the bend, right, in your upper airways. So that's what happens over here. These particles that deposit in the upper airways, they're not as important as the particles that end up in the alveolar, and that's the region. It's because they end up in the back of your throat, and what's going to happen is you end up swallowing them. So instead of ending up in your lungs, they end up in your stomach. So the process is totally different. Our digestive tract is a lot more impervious to toxins because we eat foreign objects all the time, but we don't really inhale them, right? So what happens here is that we end up with some particles, the next smaller size ends up depositing the tracheobronchial region, and then we end up with a sweet spot of small particles that haven't really been lost in higher regions of the respiratory system that make it to the alveolar region, but they're small enough to still be prone to a lot of Brownian diffusion, so they end up depositing in the alveolar region. And the reason these are particularly important, in my opinion, they're about 10 to 20 nanometers in size, is because they're small enough that they can cross over to the bloodstream. So if these particles can cross over to the bloodstream, it means they can end up anywhere in your body, right? Usually, studies done in rats where they expose the rats to a ton of metal particles and then they dissect them and do ICP-MS to try to find out where the metal ended up. They found that these particles usually end up in the liver, the heart, and the brain of rats. So we can assume that something similar would happen to us as well. So these are particularly important. And that's why I try to focus my research on particles that are smaller than 100 nanometers in size. So I told you about why they matter. Let's talk about some sources. They're everyday sources of particles. Like I said, there's a bunch of particles in the air right now where we are. Most of the traditional sources of particulate matter are related to combustion. So we know combustion creates a lot of particles. We can see them, right? Both outdoors with industry and vehicular pollution, and indoors, especially with smoking and the use of some consumer products, candles, incense, all of that stuff. Cooking itself can be considered a source of air pollution indoors. That's one of the research projects that my group is working on right now. Several consumer products and office products have been shown to emit particles. Some other types of personal care products as well. And we ourselves, we are a source of particles, right? Bioaerosols, we emit them all the time. In fact, talking is when we emit the most, so you're welcome. All right, so I talked to you about some of the sources, and today we're going to talk about one specific indoor source of particles, 3D printing or additive manufacturing. So who here has run a 3D printer before? Cool, that's the vast majority, that's awesome. So when you run a 3D printer, how does it smell?
Gives off a smell.
Yeah, it gives off this kind of acrid, plasticky, burny kind of smell, right? So you know right there that it's definitely emitting some organic compounds because you can smell them, but it's also emitting some particles that are very small, so you can't really see them unless something is going terribly wrong and it's burning. So additive manufacturing, as you may have learned already in your other courses, is any kind of bottom-up approach to build a 3D object. So you could take pieces of wood and laminate them together to build a 3D object. That would be additive manufacturing. There are many other techniques beyond what I'm going to talk about today. One that I like a lot is electron beam melting or selective laser sintering, where you can actually print with metal as your precursor material. Another really popular one that my students use a lot at CU Boulder is stereolithography, or SLA. That polymerization is another name. So they use a laser that basically hardens up this bed of liquid polymer. But really the most popular type of 3D printing technique, the one that we're usually talking about when we say 3D printer, is fused deposition modeling, right? So that means extruding a material through a moving nozzle, just like the planet over there, the Yoda head from before. One reason I really think 3D printing or additive manufacturing in general is the way of the future for manufacturing can be explained by this example that I really like. So let's think about this airplane, the Lockheed Martin F-22 Raptor. So there's been 195 of them built so far. And to think about it, we use this concept called the buy-to-fly ratio. Has anybody ever heard of it? Buy-to-fly ratio. I hadn't either. So the buy-to-fly ratio is how many pounds of material you have to buy to create how many pounds of airplane, basically. So this airplane weighs 9,000 pounds. Can you guys guess how many pounds of material we had to purchase if we were to build this airplane? More than 9, right? There's got to be some waste. Throw me a number. 18,000. So that would be a 2-to-1 buy-to-fly ratio, right? Any other guesses? Is everybody in agreement? 90,000. So a 10-to-1 buy-to-fly ratio. Who's more right? Who's on team 2-to-1? Who's on team 10-to-1? Okay, the majority is right. Yeah, the buy-to-fly ratio is 12.2-to-1. So that means somebody had to buy 110,000 pounds of raw materials to build this 9,000-pound airplane. This is particularly high for airplanes, of course, because if you think about all of the security and the confidence you have to have that this plane is not going to fall apart in the middle of the air, that leads people to want to machine every single part out of a piece of titanium. It's usually titanium, right? So a block of titanium. So I have seen when I visited national labs, people told me that Oak Ridge National Lab has a big initiative on 3D printing. So they told me that even brackets that are just holding cables inside an airplane has to be machined from a block. So you can imagine that's how you end up with this massive waste. So 3D printing can end up helping with a lot of this. I'm not saying we're gonna 3D print the entire turbine at this point, but you can 3D print moving parts. And if you start with a bed of metal powder, then your waste is almost zero, right? So this buy-to-fly ratio could significantly decrease, making the whole industry more sustainable, which I really like. So this is a pretty advanced sort of example. Obviously, we're not going to be building 3D printing airplanes anytime soon, but there are many other uses, of course, of 3D printing, as you know. Things like tailor-made medical devices to hobbyist products and models and things like that. My favorite example of popular use of 3D printers is this one. So the Smithsonian apparently will let anyone print their historical artifacts because they're 3D scanning all of them. So you'll be able to go to their website and just print whatever skull you want to play with, which is really cool. There are many other interesting engineering applications, in my opinion. There are some folks working on 3D printing entire circuits from scratch. And there's a professor, Rob McCurdy, that just got hired by my department. And when he came over to interview, we were all wowed because he brought his little robots that he had printed. So these are, an actuated robot that was 3D printed from scratch. But then, of course, in the middle of all of that, 3D printers are getting very popular. We're all very excited about it. But remember, I'm here to talk about the bad and the ugly side of it. So it all started, in my opinion, in 2013 when this guy, Brent Stevens, and his group published this paper. They found that there were a lot of particles emitted during 3D printing. So basically, they went to a maker shop, maker space in Chicago, and they printed all of these little frogs. And they saw that whenever you're printing them, this is a number of particles in the air, and this is just time. When they had a few printers running and many more printers running, they found that there were a lot of particles just being put in the air. So this is very crude, raw data just showing, hey, there's particles. We need to be looking into this. So then I got really excited, and many other researchers did too, to be like, we were just curious. We wanted to find out why these particles are being emitted. Are they dangerous? How big are they? And are there ways that we can prevent this from happening? Because if 3D printers are going to end up in every school and every home, then something needs to be done to that industry to prevent this from happening, basically. So we did our own measurements in real environments in some places at Virginia Tech, and starting in two different labs, 2 different offices, and a classroom, all of which had their own 3D printers, and they were printing their own objects. We didn't prescribe any specific activities. They just came and printed. And we found that, during background levels, concentration of particles in the rooms were much smaller, except for this day, something was going on in that building. Whenever you start printing, you can see an increase in particles. Not in every case, like here, nothing happened, here, nothing happened. That's due to the ventilation system. We don't really understand what's going on in the building. So this further showed that in real environments, in your office or in your classroom, if you're operating a 3D printer, the ventilation in the room may or may not be enough to dilute all of those particles away. So then we decided to follow up with more controlled studies inside a chamber in the lab to really understand the fundamentals of the process. So what happens here is that you have this polymeric filament, right, being extruded through a heated nozzle. The most common feedstocks are PLA, polylactic acid, and ABS. That stands for acrylonitrile butadiene styrene. And here are the monomers that make up these polymers, right? The temperature of the nozzle is usually around 250 degrees Celsius. That varies a lot from printer to printer and material to material. And what we found was from some, theoretical search in the literature, the thermal degradation of these materials starts before you reach the temperature of the nozzle. So there's definitely a possibility for these materials to be degrading as they're touching the heated nozzle, and to then break up into either their monomers or maybe some smaller molecules that are small enough to be volatile at this region, at this temperature, But once they leave that area and they reach room temperature, then they recondense back. Because these molecules might be small enough to be volatile at 250, but not enough to be volatile at 21 Celsius, which is the room temperature. Does that make sense? Cool. So there are some different theories here. Are we talking about this process I just explained, where these polymer chains, big polymer chains, are breaking into smaller chunks? Are they breaking into their monomers? In that case, they would just stay in the gas phase. They wouldn't really make particles. Or do we have something called chemical vapor deposition, where the same molecule is just evaporating and then recondensing back? So we wanted to explore those possibilities. So to do that, we did a controlled chamber study. So what we have here is our chamber is basically a glorified bag made of polyethylene, about half a cubic meter. And it has some glove access, so you can operate the 3D printer inside it. And we operate this chamber as what we call a continuously stirred tank reactor. So this is important so that we can model emissions later on. It means that we know what's coming in, we know there's something going on inside, we know what's coming out. And we know that if we measure what's coming out in terms of concentration, we assume that it's that concentration is representative of anywhere inside the chamber. So the chamber is a mixed tank. So we had a little fan, basically. Well, the printer itself has a fan, so we assume that's complete mixture. So other things we did were, we knew we were inputting clean air. So we had a filter to remove particles, we had a dryer to remove relative humidity, and then we were pulling air out of the chamber at the same time with a number of instrumentation. So the instrument on the top is the instrument that my group uses most in the lab. It's called the Scanning Mobility Particle Sizer. That's a long name just to say that it's counting particles of every different size, of different sizes. So basically it separates particles by size first, and then it counts them. And it uses an electric field to do that separation. That's why it's called scanning mobility, because it's counting them by electrical mobility. But what it matters here is that we are counting particles, and we are also sizing them at the same time. So we can tell size and concentration. And then we have this impactors, this tiny little instrument with 3 stages over here, where particles impact on a surface, and you can kind of segregate them by size too. So we had different stages, and we were looking at the smallest particles we could possibly impact there. The particles were impacted on a silicon wafer substrate, and then we took that silicon wafer to do some Raman spectroscopy analysis and scanning electron microscopy analysis. And I'll talk to you a little bit about Raman later, so you get an idea of what that is. And then that gave us some information on morphology and chemical composition. And the most boring part of this job is that we were printing this NIST part. Instead of printing fun things, we had to make the same thing over and over, and it had to be a standardized part that if others are printing for their own studies, hopefully we can compare results a little better. So we talked to other groups that were doing this kind of research, and they're like, oh, we're going to print the NIST standard part. So we did that too. This part was developed by NIST to really test the ability of the printer itself on being able to make the features. So it has negative features on the side here. It has positive features on the top and negative features on the top as well. So it's basically testing the printer's ability to make those. It's not really developed for testing aerosol emissions, and that's associated with its own problems. But I'm all for standardization, so that's what we were printing over and over again. So let's get to some results. So what you see here are the emissions of particles that we modeled, assuming that that chamber is a continuously stirred tank reactor, as I mentioned before, for the entire printing process. So before you start printing, it's background levels. There's nothing going on in the chamber. The chamber is clean, free of particles. The moment you start printing, you see this really big spike in emissions. And the first thing you may notice here is that we have 2 panels here for our result. These are for different materials that we were printing, different types of filaments. And that's because I couldn't plot these data on the same plot. As you'll see, the y-axis is totally different, right? We're going 10 to the 8 particles per minute, and this is 10 to the 11. So there was a 2-order magnitude difference depending on the type of filament that you're printing with. So our highest emitting was, as other works have shown multiple times, ABS is by far the highest emitting. So here's ABS value, the orange. In gray, here's ABS premium, which was very similar to PLA in terms of emissions. And then over here were some special TPLA filaments that we got This one was infused with copper, and this one was infused with wood. If you remember back the Yoda head that was playing in the GIF, it looked kind of like wood. So it was this kind of wood-infused PLA that it was printing with. And these had much, much lower emissions, 2 orders of magnitude lower over time. The other interesting thing you may notice is that we tested 2 different types of ABS, and they had drastically different emissions. And the interesting thing is that ABS value was way more. It emitted much more than ABS premium, and ABS value, as you can imagine, is the cheaper. So cheaper is, in this case, is far worse. I don't know about the quality, the mechanical properties of the part itself, but in terms of emissions, it was much, much worse. We also noticed that there was a lot of emissions in the beginning for both all these 3 cases, and not so much towards the end of the print job. So something happens at the start that maybe the nozzle overheats, or maybe it's the way that it prints the bed in the bottom of the print job. You know how it has that sometimes, depending on the printer, they have a really big raft. So when it's printing that raft, we have a moment of highest emissions. I wonder if it's because the nozzle is also pressing against the surface to create that raft. This is all conjecture. We're trying to figure out why exactly that's the case. We don't really know. There were some moments of higher emissions towards the end, and we might think that that's because our part has some interesting features at the end, so that may have enhanced emissions. We're not sure. But when we printed with the copper and wood infused, then it was total, especially the copper infused was totally different. And you'll see later how copper emissions were very different than all of the rest. So here I'm showing you how many particles are emitted per minute, every minute you're using the 3D printer. Next, I'm going to show you what happens at this moment here. So if we just look at the moment of highest emission, we want to know what that looks like. So what you see here is the size distribution of the particles. So the x-axis now is no longer time. Now we're talking about the size of the particles and the relative amount in each size. Basically, that's what this means. So that's the size distribution of particles. So again, the value line, the cheaper ABS, had the highest concentrations, highest emissions as well. And the particles were about 50 nanometers in size, so fairly small and smaller, of course. The premium ABS had exactly the same mode. So particles were they looked about the same, but there were fewer of them. Does that make sense? For PLA, emissions were, in terms of numbers, they were pretty similar to ABS, remember from the previous chart. But these particles were way smaller, about 20 nanometers in size. For the wood-infused particles, we also had, this mode of particles, 20, 30 nanometers in size, pretty small, and there's so few of them, it was hard to really tell. But for copper, as I mentioned before, emissions were totally different. These particles, I had to use a different instrument to get to the size range. These particles were not below 100 nanometers. In fact, they were all above 100 nanometers. And they were about 4 to 500 nanometers in size on average. We think something really cool, interesting could be happening here, that the copper itself is acting as a catalyst and making particles grow and get bigger, which could be a really interesting solution to the problem. If we make the particles bigger, then they're less of a health concern. But at this point, like I said, this is all theory. What we know is that the copper printer consistently showed that particles were bigger. These shaded regions, I didn't explain before, they represent standard error. So they basically are showing that we did this many times and we kept getting consistently the same type of results. So now that we know the size of the particles and how many particles are being emitted, then we can model the inhalation dose. Basically, how many particles will end up in your respiratory tract, right? As I was talking in the beginning of the talk. So if you were to print a part for 1 hour, so I know these printers usually run for, I don't know, overnight, over 10 hours sometimes, but say that during the 1 hour print job, you're standing next to the printer, maybe you have it right next to your desk in your office. So about 2% of those particles would actually stick to the alveolar system. Like I said, many of them we inhale and then exhale them back out. And then 0.7% would end up in the tracheobronchial region, and only 0.4% would end up in the upper airways. You would inhale about 10 to the 10 particles, or 6 micrograms, and that's really not a lot, but as I mentioned, it's one time, 1 hour, right? It's not every day or 12 hours or something like that. Then you can multiply it. So your dose here would be smaller than if you were sitting right next to candles or incense burning. That's really sooty stuff that you can actually tell. Yeah,
Does this have a cumulative effect?
Yes. Particles in general have a cumulative effect.
Right, so in this process then, if I do this an hour and then I come back 2 days later, I've got the 6.2 and then I'm gonna have another 6.2. So in the end, what is my bad worst case scenario? I mean, other than I now have an OSHA issue or a health concern.
Yeah, so exactly. So that's the thing with air pollution. There's acute effects, health effects. There are issues if the air quality all of a sudden is really bad today, and you already have issues, cardiovascular, respiratory issues. Then it could lead to a really bad effect. But the majority of air pollution issues are about chronic exposure. So if you're exposed to air pollution chronically, then you may end up leading to the effects that I talked in the beginning of the talk, where life is decreased and quality of life is decreased as well. So yeah, exactly. This is the dose for 1 hour once in your life. But every time you do it, you can just multiply by what we're counting here. So that would be the same as sitting next to candles or less than candles or incense. But it would be more like the same as, more similar to exposure to an electric heater or laser printers. Those have also been shown to emit a lot of particles. So we were trying to investigate what the particles are actually made of, and I'll go through this part rather quickly. So as I mentioned before, we collected these particles, so we impacted them on this silicon wafer substrate, right? So that's the pink that you see, that's the background. And you can see sort of this splatter image because we were trying to impact as much of these particles as possible. Let them accumulate there, get a lot of mass because as you know, these tiny particles end up amounting to no mass. So we did this for several hours to get as many particles on it as we could, and we took to something called Raman spectroscopy. Who here has ever heard of Raman spectroscopy? It's not a super common analytical technique. It basically looks at the interaction of samples with light, and it's a vibrational spectroscopy type of spectroscopy. So it looks at the interaction of the samples with light to get us an idea of the bonds that are present in a material. So basically, you cannot detect that there's nitrogen there or there's carbon, but I can find a peak that corresponds to that particular bond there, the triple bond between a carbon and a nitrogen. Does that make sense? So it's a lot less direct, right? We're just looking at these specific bonds. I cannot tell the elemental composition directly. But we took it to Raman spectroscopy because it's a non-destructive technique. It doesn't involve any heat. These are the products of thermal degradation. So if we took it to any analytical technique that heats them up, they could further break apart and transform into something else. So we looked at some big particles from the edges. We looked at some small particles from the beginning. And these are the spectra that you see. We also looked at the raw ABS. So this is before printing. We looked at the part that was printed in red, the 3D product. And these are our little particles, the aerosols or particulate matter. So there are two peaks that are very important here. These 3 peaks here, 1, 2, 3, they relate, actually 5, but the 3 major ones, they are characteristic peaks for the benzene ring. So we can tell that if a sample has those 3, it has the benzene ring. So the raw ABS had it, the 3D part had it, we couldn't really find it in the aerosol, right, in the particulate matter. They weren't really there. So that showed us that the styrene was not present in the aerosol from ABS. And then there's another peak that's important too, and that's that triple bonded carbon with the nitrogen that I mentioned before. We know that that peak is representative of it, and here it is in the raw ABS, in the 3D product, but it's not there in the aerosol. So that kind of shows us a theory that these particles are not made of ABS because they don't have this and they don't have this. It's possible that we were just not able to detect it through Raman. It's possible that there's so little of them that we weren't able to see it. But it's kind of telling us that these particles are made of something else because they have all of these peaks. For the really tiny ones, it was a lot harder, of course, to get a clear signal. But for the bigger particles, we can tell that there's something else. It would take a lot of extra effort to find out exactly what. So we have a lot of theories, a lot of working hypotheses. The first thing I mentioned to you was that chemical vapor deposition theory, that maybe the ABS is just evaporating and then recondensing. And I think we were able to disprove that by showing that those peaks just weren't there. And then another possibility is the thermal degradation of the ABS, which is then recondensing onto particles. And then for that, we know that there's some data showing that the polymer itself can thermally degrade at smaller temperature, at lower temperatures, but these three monomers, it takes much higher temperatures for them to degrade themselves. Printing, again, happens at around 250, 270 Celsius. There is a work that showed that if you spent a very long time at lower temperatures, you could thermally degrade the butadiene or other compounds as well. Other works have shown that there are many, a plethora of emissions from gases and particles from 3D printers. So they showed a variety of volatile organic compounds. Those are all pretty light, so they wouldn't be turning into particles at room temperature. But some are meant to be liquid at room temperature, so it's possible that these polymers were breaking into these smaller parts that then turned into droplets in the air. For PLA, similar story. There are many volatile organic compounds, some compounds that are meant to be liquid at room temperature, and some compounds that are actually meant to be solid at room temperature. So it's possible we're just breaking them into a variety of compounds, not just a category or two of compounds. So that theory of the thermal degradation definitely holds, and then that there's condensation happening afterwards. And then there's another theory that I kind of like. When you're all using the 3D printers, the filament comes in different colors, right? And there's some filaments that are flexible and some filaments that are electrically conductive. The way they're able to do all that is by the addition of additives, right? They're lubricants, antioxidants, pigments. They can oxidize, they can degrade, and they can volatilize. So maybe it could be these completely unknown, because we asked the manufacturers and they're not going to tell us, completely unknown, huge category of compounds that are also present in the filament. The filament is not pure ABS or pure PLA. So further work that we've been doing at CU Boulder is looking at the electrocarbon content. So we found that there is no soot basically being emitted as expected because temperature is rather low. All of the carbon is organic. ABS emits a lot more than PLA, as we all know, and both more than the background, of course. And we've been doing some of our own VOC emissions testing and figuring out what's in the gas phase itself. So for these volatile organic compounds, we found at least three compounds. One is styrene, of course, it's one of the monomers right there. One butanol, which could be coming from any of these, but mostly probably from the butadiene, I don't know. And then this thing called oxyrane that I had never heard of before. And then when we tested the ABS, that was for PLA. When we tested the ABS, there it is again, the oxyrane. That's for ABS, and that's for PLA. And there it is again, oxyrane. So then, for further investigation, we went to Wikipedia, and we found, and there it is, oxyrane. It's on Wikipedia. It's used for many consumer products, so it's an additive. But it doesn't go in the consumer product as oxyrane. It actually goes in the products as ethylene glycol. It's part of polysorbate 20, polyethylene glycol. We know these, right? These are in a variety of consumer products. So the interesting thing here is that oxyrane itself is not safe at all. It's flammable, carcinogenic, These are safe. These are less toxic and more safe. But then once you put them in the filament and you run it through a 3D printer, it's possible that these are breaking back into oxyrane, the precursor molecule, and emitting it, which I find rather interesting. So even though my research mostly focuses on particles, we are also looking into the gas phase for the volatile organic compounds, because they're also very important, as you can see from here. They're also very important for human health. So basically, our further investigations will include volatile organic compounds and look at some specific additives to see if they can change the way particles are being emitted, look at additives like copper, for example, to see if that can change the way particles are emitted and the amounts, and try to collaborate with people that will try to develop lower emission feedstocks, which would be really interesting. And also collaborate with inhalation toxicity studies. There are some people doing already some works to show that these particles do have some toxicity associated to them as well, not just the gases that have known toxicity. That's pretty much what I had for today. I'd like to acknowledge a lot of colleagues from Virginia Tech. A lot of this work was done before I moved to CU Boulder, and then it continued on at CU Boulder with other colleagues. It was funded by Virginia Tech and a few other centers. So with that, I'd be happy to take any other questions you guys may have.
Thank our speaker.